This video is for physics. Today you're going to be getting the basic formulas for mechanical energy, kinetic energy, and gravitational potential energy. And you're also going to be doing what I call the line writer activity. All right, so let's go ahead and set you guys up for that activity that you're going to work on by introducing some equations for some of the ideas that I have mentioned. You guys have learned about some various energy ideas, but we're going to get much more specific now. Okay? And for this class, we're going to start with what mechanical energy is made up of. For this class, if you continue in physics, there'll be additional things that get added on here. Like if you take AP Physics 1, rotational kinetic energy will pop up, and then eventually in AP 2, electric potential energy. But for our intro physics course, we're going to just consider mechanical energy to be made up of two things: kinetic energy and gravitational potential energy. Now, I'm not putting a GPE here. Just know that that potential energy is gravitational potential energy. So if you take the gravitational potential energy of an object and you add it to its kinetic energy, you will get its mechanical energy. Okay, so now your question is, all right, so ME is just those two things added up. What are those two things? Let me get a formula on for you, formulas for both of those, and then we will discuss a little bit more. So kinetic energy equals 1/2 the mass of the object times its speed squared. Okay, even if you say this is 1/2 mass times velocity squared, you got the squared there, so you're losing the sign part of it. Okay, these energy ideas are scalars. Okay, they're just the amount of something, so you don't have to worry about directions. These are all scalars. Okay, so this is 1/2 mass of the object times its speed squared. So what does that mean? Well, if an object is not moving, its kinetic energy will be 0. If it's moving at a slow speed, it'll have a little bit of kinetic energy. If it's moving really fast, it'll have a lot of kinetic energy compared to when it was moving slow, because we are varying by the square of the speed. So every doubling in speed, assuming the mass stays the same, every doubling of speed, for example, would cause the kinetic energy to go up by a factor of 4. Okay, you triple the speed, you get 3v squared, like you have to have the parentheses there, it would go up by a factor of 9. It's varying by the square. Okay, and you've heard the word kinetic in some context before. So if you remember the motion equations, those were also called the kinematic equations. So this idea of kinetic energy, you may have heard of kinetic theory when you're doing your chemistry stuff. We're talking about things that are moving when we say kinetic. So kinetic energy, that's the energy that we're associating with the movement of the object. Okay, so what about this potential energy? Well, potential has to do with something being, in quotes, stored. So you can think of potential energy as stored energy. And in particular, this is the equation for gravitational potential energy. It'll be the mass of the object, assuming we're near the surface of the Earth. It'll be the mass of the object times 9.8 meters per second squared, if we're near the surface of the Earth, our gravitational acceleration due to gravity, times the height. Okay? So and now you have to define where a height is 0 for this to mean anything, but let's say that my laptop here is a height of 0, and I've got, what do I want to drop? I don't really want to drop my stylus. Let me grab something that won't hurt my laptop either. Here, we'll drop this game case thing. All right, so if I have this here at a certain height, there's a height from here to here. Okay, if this is a height of 0, that has some gravitational potential energy. It's got some stored energy, because if I let go, okay, it will start to fall downward. We're looking at this not from our motion force stuff, but from an energy standpoint. Okay, and as it falls down, okay, the potential energy goes down, because it's getting lower and lower and lower. As it's falling down and getting lower and lower and closer to a height of 0, the kinetic energy is going up, because as it falls, it will go faster and faster and faster. So for this process, if we neglect air resistance, this actually stays the same, the mechanical energy. What happens is, when it starts off here and it's not moving, it would have a kinetic energy of 0. It would have a potential energy of all of it, okay, whatever that value is. And then as it's falling, it's going to go faster and faster down. So the KE is going to go up, but it's getting lower. So the potential energy is going to go down. So if this stays the same, which it does for this process while it's in the air, not when it hits this, okay? While it's in the air, while it's falling, okay? If this stays the same, when one thing goes down, the other thing has to go up to keep that number the same, or for mechanical energy to be conserved. All right? When does this stay the same? This next part I'm going to do here, I'm going to put it in like a little dotted line, dotted circle area. This is not something that after today that you're going to need to worry about much, okay, for this class. But if you continue, this will matter. So there's some lingo on here that I'm going to say, but I'm not going to fully explain this. I'll give you an easier version to hang on to here in a minute. But the true condition for when mechanical energy is conserved is when the work done by something called non-conservative forces is zero, okay? So what does that mean for us, okay? Well, in this class, as long as you've got something that is traveling along without any collisions, so no collisions, no bumps in the road if it's something sliding along, and we can neglect friction and air resistance, you can assume that the mechanical energy of that object will stay the same. Like I said, it's a little bit more involved than that, but for this class, you can think of as if we've got smooth surface, no friction, no air resistance, no air resistance. I should also mention no air resistance and nobody like pushing on the object, okay? Then that work done by non-conservative forces will be zero and our change in ME will be zero. Again, don't sweat that too much. The problems are basically, they're gonna tell you, or it'll be clear that ME is conserved in the problems that we're gonna do. We're only gonna do, I think, 3 on Tuesday. Enough of that little disclaimer kind of stuff there, okay? Units too here, before I forget. We've got newtons times a meter would be one way to do this, Newton times a meter. As you'll see here, M times G, mass times acceleration would be a force, so that's Newton times a meter. That's the unit of any of these energies, or another way to write it, a Newton times a meter can be abbreviated as a joule, okay? So Newton times a meter or a joule, or if you're like putting everything into base units, I'll expand this out here a little bit, and you don't really need to sweat this too much. You can just throw the units on there. We're not gonna have too much to worry about with units on this, okay? But a Newton is a kilogram times a meter per second squared, and then times a meter. So this is, or you could write it like this, or kilogram times meter squared per second squared. So all these are fine. Typically, most people are gonna write Newton times a meter or a joule. And now let's go ahead and take a look at the line writer before we start doing our bar graphs. Let's see here, I have this pulled up, should have this pulled up. Yep, okay, all right. So you'll need, linewriter.com is fine, or if you do a Google search for line writer, for some reason that one's blocked on your school computer, just scroll down the Google search list, click on the line writer ones until you get something that looks like this, okay? It'll open up, there'll be some stuff up here, some stuff on the sides, that type of thing, okay? And I've made a track here that is not good, so let me go ahead and hit play here. You would not want to make one that looks like this, because that is not smooth, okay? Line writer came down here, and now he's doing all sorts of weird stuff, but line writer came down here and crashed. We don't want any collisions for this activity. So the link for the activity is on the tweet, okay? And I'll give you directions, but I'm gonna show you here a little bit about this. So let me go ahead and do a new, and your version of this might look a little bit different depending on where you got it, which link you clicked on. But I'm going to make a new one. Up here at the top, all these line writer things have different options. You do not want any red parts, because red parts will give him a push, they'll give him a boost, they'll make his ME go up, and we don't want that. For this activity, we are assuming that mechanical energy, the first page, the page you're doing, the mechanical energy stays the same, that it is conserved. So we don't want to give him a push. We want him to just be sliding along, with no friction, no air resistance is the assumption that we're making. No friction, no air resistance, and no pushes, okay? And no collisions either. We don't want any bumps in the road, okay? So how do you make a track here to go along with your activity? Well, blue part, the pen, it's already clicked. And then, am I going to need to use my mouse? No, I think I can use my stylus, okay? I'm also going to move this around a little bit here. Let me zoom out. I want to zoom out some. Zoom out, and then I'm going to click on that thing to move it around. You can play around with this for a few minutes before you, you can play around with this for a few minutes before you, take 5-10 minutes, just mess around a little bit until you're ready to make your actual track, okay? Also, I should mention green parts are fine because they're just art, okay? They're not going to add any actual track. And the direction you draw the track matters. Again, don't use red tracks. There's lots of other options on here. You don't need anything super complicated. So an example of a track that you could use here on this, you just want it to be smooth, you could basically just do something like that, okay? If you want to make it more involved, if you want to do something like that type of deal, except make sure this is smooth, that's fine as well. Okay, I'm going to go ahead and hit play here and see if he travels along pretty smoothly. Yeah, that would work. Okay, so something like that would work. So let me go ahead and hit stop. All right. And one of the things you'll have to do is take a screenshot of your track that you're using for the actual activity, but you'll have to pick 3 locations on your track to think about mechanical energy, kinetic energy, and gravitational potential energy. So let me go ahead and switch over back to OneNote. All right, so I'm going to go ahead and draw my track on here. Okay, and here's my little guy. There's line writer. So here's 1. Maybe at the bottom is where I'm going to pick 2. And then maybe over here somewhere is 3. But this is up to you. You can pick anywhere that he makes it to is fine. And the line writer part, where you're doing the visual, is for that very reason, okay? You're actually going to write your answers somewhere else. Draw the picture. You can do it in OneNote. You can do it on a piece of paper. But draw a picture of your setup and answer the question somewhere other than on the actual line writer. Occasionally students will do that in class. When we do this in class, we'll be like, no, put it somewhere else. So that it'll be easy to turn in and it won't accidentally go away or anything like that. You just need the line writer track where you hit play for a visual so you can think about some questions that you're going to ask yourself that go along with that on how to draw these bar graphs. Okay, so let me go ahead now. The next thing we'll do is, and follow the directions in the document, these will be recapped there, but we do need to define where h equals 0. And when we're eventually going to do problems and put numbers into this stuff, the spot that you will define to be 0 will be the lowest spot in the problem that you care about. So for me, that's at the bottom of this hill. So I'm calling right here a height of 0. So that's a height of 0. And now we're going to do our bar graphs, okay? And we're going to ask ourselves some questions. So you will need to think about these formulas. We're not plugging any numbers, okay? But you will need to think about these formulas when you're drawing your bar graphs. For example, if he's not moving, well, what will his kinetic energy be? If he's not moving, this will be 0, Ke will be 0. What if he has a height of 0? What if he's at the lowest spot? Then he won't have any potential energy, any gravitational potential energy, okay? So that kind of thing. You do need to ask yourself some questions. Is he moving? Is he moving fast? Is he moving slow? Does he have a height? Okay, is his height 0? That's how your brain should be working on this. And this picture and the visual to go along with it, with the guy sliding along, will help with that, okay? By the way, it's just a simulation. Line writer is not perfect. No matter how great you make that slope, eventually he's going to slow down and come to a stop, so ME will not be conserved. But we're assuming for our activity that it is, okay? All right, now let's go ahead and draw some bar graphs. So what do I mean when I say 3 sets of bar graphs? So we're going to draw bar graphs for ME, KE, and PE at spot 1 on its own. Then separately on the page, we'll draw bar graphs for ME and KE and PE for 2, and ME, KE, and PE for 3 somewhere else on the page. So at the end of this, you should have 9 bars on your paper, and it'll be 3 sets of 3. So 3 bar graphs, okay, or a bar graph with 3 bars on it, then a separate thing with 3 bars on it. So for example, let me go ahead and do segment 1 here. So this is for 1, for my number 1 there. I'm going to write down here at the bottom, ME, KE, and PE. And as a reminder, I encourage you to write ME equals KE plus PE as you're doing that, just to remind yourself. I'm going to do this, okay? And now I'm going to draw some bars to represent the values of this. And remember, we're assuming that ME stays the same. So our bar graph for ME from 1 to 2 to 3 should stay the same, okay? And if it helps you, you can put numbers on the top of the bar graph, or if you are messy, please put some made-up numbers on the top of the bar graph. So if you draw like me, you're going to want to do that, okay? All right, so I'm going to start off and make up something for how much mechanical energy he has at the beginning, and I'm just going to call that 10 joules. So he's got 10 joules of mechanical energy at spot 1, and I just made that up, okay? I'm just saying he has some, okay? Now, why does he have some? Well, at spot 1, that's when I first hit play. He wasn't moving, so my kinetic energy is just going to be 0. Why? He's not moving. He's not moving. At segment 1 then, if these two have to add up to 10, it's all potential energy. Why does he have potential energy at spot 1? Because there's a height. He is above the ground. There's some stored energy, okay? He's got a height, so there's some stored energy. I'll go back here and show you the equations. Because we have height, we have PE. Because we're not moving, this is 0, we have 0 KE. So there's my 3 bar graphs for spot 1. Now, for spot 2 and for spot 3, you would do the same type of thing. And depending how good you guys do with this, I mean, if you all get it right, I won't worry about this. But if people have any problems when I check your bar graphs, I will fill in 2 and 3, and then probably link to it, or maybe email the 1 or 2 people maybe that need it to take a look at it for 2 and 3. But at 2, I would then do a bar graph for ME, bar graph for KE, bar graph for BE, and same thing for 3. If you're like, oh, I don't know which one's supposed to be bigger, KE or PE, that's fine. It's just a judgment call. Okay, just make sure it makes sense with what's going on in the problem. So then you would put bar graphs at 2 and 3. I'll go ahead and put my ME on here. This will stay 10, and this will stay 10. So 10, 10, 10. Now, if you're lining these up and you're super neat, okay, and it's obvious that these are all the same height for ME, that's fine. But otherwise, yeah, throw some numbers on there that you make up just to make it a little bit easier when you look back at it, and for me to check to make sure your answers make sense. So that's what you'll be doing, 3 sets of bar graphs for that. A quick recap of our ideas here about 1 going up, 1 going down. When you are, the reason we're doing bar graphs for this is because I'm not a huge fan of bar graphs. But there are a few places where they are very beneficial, and this is one of them. When you've got one value going down and the other value going up, it helps to picture the bar graphs where one value is dropping, the other value is going up. So you can picture the transition between like 1 and 2 as that PE goes down. Whatever it goes down by, that KE is going to have to go up by as we go from segment 1 to segment 2. So bar graphs are beneficial. And if you have a tough time picturing the transitions of what would happen in between, I have some PhET simulations I can link to with pendulum swinging back and forth, which can help you wrap your head around or visualize what's going on with as one goes down, the other goes up. That's it. Good luck with your line rider thing. If you have questions, let me know.